Okay. So we're going to continue our discussion of the heart. And I know we're going through this stuff kind of at warp speed, so I will make sure to put an extra kind of practice quiz assignment stuff for you to take a look at this weekend so that we can stay on top of it. And today, as we talk about this like ion and depolarization stuff, I'm going to highlight for you a couple of just like important things. We're going to go less into detail about this stuff than it may look on the slides. And I'm going to consider this a less important emphasis than when we're talking about ion movements in like our neurons and our muscle cells. But we do want to know like how and why this is different than what we've seen before. Okay, so when we left off, we were talking about pacemaker cells, which are part of our electrical system in the heart, so part of our conduction system. And the cool thing about pacemakers is that they are autorhythmic because they have pacemaker potentials. So they're creating the rhythm of your heart through their spontaneous depolarizations. Okay. So what is important here for our pacemaker cells in particular is going to be that we now have a much bigger role for calcium than we have seen before. And we've seen calcium in the past. We saw it in our neurons when we were releasing our neurotransmitters. We saw it in our muscle cells when we were talking about cross-bridge cycling. But now we see calcium really involved a lot in this depolarization in the heart. So we do have sodium and potassium still involved in the initial depolarization and in the repolarization at the end. But calcium is a lot of what's going to be driving these action potentials in the heart. Okay, so if we're looking at the action potential in our pacemaker cells, so you want to pay attention to the labels, right? So we're looking at a figure about pacemaker cells. And I'm pointing this out because this is going to be different than the myocardial cells, than the like heart muscle cells. This is specifically about those electrical cells, those pacemaker cells. So we can see that their action potential looks similar-ish to what we saw in our nerves, right? So we see that we have an initial depolarization, but this is now happening just like as a wave automatically, this autorhythmic quality. We then see a rapid depolarization and repolarization. Oops, should grab that circle lower, sorry. And then it happens again. Okay. Now, these are due to ion movements as before. So we're just going to pair those up. And because the colors are kind of blurry on here, right? So this first part of that slow depolarization is happening because we have increases in the permeability to sodium, which comes into cells, positive ion, so it depolarizes. And the permeability to potassium is decreasing, so potassium isn't escaping, it's getting stuck inside the cell, so also adding into that depolarization. But then what we see happening next is where we bring in our calcium, right? So this little bit of our depolarization is where we see our permeability to calcium starting to increase as we're turning off that permeability to sodium. And then we have a really rapid depolarization due to calcium rather than sodium. So when we saw a curve like this, our action potential in a neuron, this spike was because of opening voltage-gated sodium channels. This is now because we have our calcium coming in. Okay. So that's our big difference when we're looking at this action potential in our pacemaker cells, is that this spike of the action potential is due to the opening of calcium channels rather than sodium channels. Okay. To repolarize, we just turn all these signals off, right? So for the rest of this action potential, we see that we turn off that permeability to calcium, and we let our potassium escape the cell again. Okay, so that bit is similar to what we saw in our neurons. Okay. Now, it's not just our electrical cells that have to depolarize. We do have to depolarize the heart muscle itself, right? So the electrical signals just send that electrical pathway from our pacemaker cells in the sinoatrial node to the AV node, then to our bundle of His, our right and left bundle branches, and then up the Purkinje fibers. But the point of doing that was that we get the right muscle cells to contract in the right order. So this next bit is about contractile cells. Okay, so this is the muscle cells really that we're looking at. Okay, so we didn't focus on numbered phases for those pacemaker cells, but we do have numbered phases associated with the cardiac contractile cells, so the muscle parts. Okay, so at the beginning, we do see changes to sodium permeability. So we see a phase 0 where we have some permeability to sodium. But then we're going to see calcium playing a big role here as well. So in phase 2, we see we've got increased permeability to calcium. Okay, we're changing potassium stuff as well before we go back to rest. Okay. So this is going to be also of a different length than we saw action potential in skeletal muscle. So in skeletal muscle, we had a duration of about 1 to 2 milliseconds. So that was pretty fast. But for our cardiac cells, this takes a bit longer. So here we are looking at those phases. Okay. So first we have some sodium coming in, right, in this stage 0. Okay. Then we see changes to our depolarization as we stop letting sodium come in. Okay, so brief repolarization. Then we have a plateau. We're trying to make up for the fact that sodium isn't coming in anymore by letting calcium in. Okay, and then in our repolarization phase here, we let our potassium escape and turn off that calcium again. So comparing the two, when we're comparing action potentials in the heart overall versus in our neurons, we see a bigger role for calcium. That role of calcium is particularly strong in the pacemaker cells, creating that pacemaker potential. Okay. It is present in the contractile cells. So some of this has to do with permeability to calcium, but sodium plays a big role in these muscle cells as well, in the contractile cells. And that's our overall summary of what we want to know. So in terms of excitation contraction coupling for those cardiac contractile cells, so the cardiac muscle itself, we're going to see some ways in which cardiac muscle is similar to our skeletal muscle that we talked about in our last unit, and some ways in which it's similar to our smooth muscle, which is what we have surrounding our blood vessels. Okay, so some of the features, a lot of the features are going to be things that we've seen before. So we're going to see that we have T-tubules conducting action potentials. We have a sarcoplasmic reticulum that stores calcium. We're using this troponin and tropomyosin system in order to actually cause contraction, right, by binding calcium to troponin, pushing tropomyosin off of our contractile proteins, our actin. Okay. But things that we didn't see in our skeletal muscle that we do see in our cardiac muscle, okay, are going to be that we have gap junctions, and we have some of the calcium coming from outside the cell. Okay, so in our skeletal muscle, all of that calcium came from the sarcoplasmic reticulum. Now in the heart, we have some of it coming from outside the heart. Okay. So here's a big picture view of what is happening. I do not expect you to memorize all these steps, but I'm just going to point out a couple of things going on here. And I can send out an exact summary of what I would expect you to know versus not at the end of class. Okay. Great. So one is that to create our depolarization, right, we have gap junctions between our cells. So we haven't seen these cytoplasm to cytoplasm tubes in our muscle before, at least not when we were concentrating on our skeletal muscle. But now this is important for the waves of depolarization that we see in the heart, because we really want our heart muscle to kind of contract together. So this is a really fast kind of communication here. That depolarization spreads along the membrane like it did in our muscle cells, or skeletal muscle cells. But now we can see that extracellular calcium comes in here into the heart muscle, which was not true in skeletal muscle. So ultimately, when you think about how the heart functions and you're thinking about like medications and diet and pathology, right, it's important to realize that calcium has a big influence on the heart. Okay, so here we see that extracellular calcium. Okay. Action potential is continuing, right? It went down this T tubule, right, going into the cell. We do still have calcium coming from the sarcoplasmic reticulum. Okay, so that's the same as in the skeletal muscle. And we see the same whole cross-bridge system that we saw in our muscle cells. So we're not going through that cross-bridge cycle again now, but you can see that that is pretty much the same here. Okay. So at the end, some of that calcium is going back into the sarcoplasmic reticulum to be used later. Some of it is actively leaving the cell. So some of that calcium leaves at the end. So calcium fully leaving the cell is also different than skeletal muscle. So we're going to skip through this step by step, right? But what we're focusing on is that some of that calcium is entering and leaving the cell. We have gap junctions. Otherwise, what's going on inside our cardiac muscle cell is similar to the skeletal muscle. Okay. So in terms of rest, how we let the heart rest, like in our skeletal muscle, we have to make it so that we don't have so much calcium swirling around in our cytosol. So we have ways to transport that calcium out of the cell. So we have pumps, basically, an ATP ACE, so something that uses ATP, breaks it for energy. ACE is that enzyme ending. So we break ATP for energy in order to transport calcium back into the sarcoplasmic reticulum. We also have a pump that pumps calcium out of the cell into our extracellular fluid when we're thinking about cardiac muscle. Sometimes we also exchange sodium and calcium for each other. Then we just go back to the beginning, actin and myosin unable to bind because the tropomyosin covers the myosin binding sites on the actin. So that part is the same as before. Okay. So you can record the overall electrical activity of the heart. So an electrical cardiogram, so like an EKG, is recorded by electrodes on the skin. And what we're trying to do is test for these conduction of electrical signals in our heart. It's nice that this is non-invasive, so you can just put electrodes on the skin to figure out what's going with this flow of charges in the heart. Okay. So this is an external measure of that electrical activity in which your body is acting as a conductor. So like the currents on the body are spreading through the body, which is mainly water, spreading to the surface. And then you can actually sense them on the surface and do some math and some triangulation to figure out where that electrical current is and when. So this is how a lot of different electrical signal recordings work. So ECG and EKG are the same thing. The K just comes from how you spell cardio in German. EMG and EEG. So when you're looking at like muscles, brain waves, all these things work kind of the same in that you're using the body as a conductor to sense electrical signaling somewhere in the heart, or sorry, somewhere in the body. We can do this because it's kind of predictable how the electrical waves will travel. So the distance and the amplitude of the spread, so like how high the peaks are, depends on the size of the potentials and depends on how synchronized potentials are within the heart, okay? And the heart, fortunately, is very synchronized, which is part of why we can sense it and do it so well. All right. So what we are doing when we're recording an ECG, EKG, the electrical activity of the heart, okay, is we're trying to figure out what in the heart is depolarizing, what is repolarizing at any given point in time, right? So the readout from an EKG will look something like this, right? This is typical, this is normal, what it'll look like, right? So this is not exactly the same thing as the membrane potential that's happening in the heart muscle itself, which is what we see in A. So that's what we were looking at when we were looking at those phases and the ion movement. But this is what we will see if we are recording in the body overall, which will tell us something about what's happening in our atria, so those chambers at the top of the heart, and what's happening in the ventricles, so those two chambers at the lower part of the heart, which contract at different times, which is part of what kind of causes this complexity. Okay, so we always have these letters in the same order. So we have P, Q, R, S, T are the identifiable kind of points here on our ECG. So the P wave is this first little peak. Okay. And what this P wave is indicating is that the atria are depolarizing. So the atria are smaller than the ventricles, right? They're just depolarizing and contracting to help squeeze the blood that's been pooling in them into the ventricles. So that's part of why, or at least how you can remember that this little peak is our atria. We're going to think about our QRS complex as kind of one thing. Okay. So the QRS complex is referring to this dip, the Q, the peak, which is the R, and then that dip, and going back to this kind of resting, that's the S. Okay. So what's happening here is that those atria that depolarized during the P wave are now repolarizing. And then we have the ventricles depolarize, right? So you can think about, right, we had a little peak for atrial depolarization. We can think of this big peak as like ventricular depolarization, and the little dip here as having to do with that peak from the atria kind of going back down before the ventricles actually depolarize themselves. Okay. Finally, at the end, we have the ventricles repolarize, and we actually see a little peak there at the same time. Okay. The reason we care about these things, right, is that this can help us figure out like how long are our ventricles contracting? How long of a gap is there between when our atria and our ventricles contract? How much space is there between heartbeats, right? Because we know what each of these little peaks and valleys should look like and what they mean, that means that we can diagnose like abnormal heart rhythms, basically. Okay. So what is happening between P and Q here? Okay. This is basically the AV nodal delay. So this is how long it takes kind of for that charge to spread and then pause as it's going from the sinoatrial node to the AV node, which is what leads us into the electrical signaling in the ventricles. Overall, we separate parts of our contractions into systole and diastole. Those are two important words for what's going on with the contraction in the heart. Okay, so systole is going to have to do with the contraction of ventricles. Diastole is going to have to do with the rest state for ventricles, right? So how long is your heart contracting? How long is your heart at rest? Are you getting enough rest? Are you contracting fast enough? Okay. So if we want to know how long systole is taking, that ventricular contraction overall, we can look from Q, which is right at the start of where we see that depolarization of the ventricles, to T, which is when we see those ventricles repolarizing. Okay. So that QT interval is corresponding to ventricular systole. And then from T all the way until the next Q, okay, that's diastole. Okay. So systole here for contraction, diastole here for that relaxation. So you can see that your heart actually should be at rest for longer than it is contracting. You don't want your heart to get too tired, right? So it's important that we have enough of a rest phase. And during diastole is also when we see the heart pretty much like filling with blood, right? So it's also important that that period is long enough so that you can get enough blood into the heart during that relaxation. Okay, so we're going to talk about the cardiac cycle. And this is a part that we do want to know in detail. Okay. So we're thinking in the cardiac cycle about the relationship between pressure and volume. We're also going to be thinking about specifically where in the heart are we? Where is that pressure occurring? How much blood is in that chamber at that time? Okay. So we're going to see that we have multiple phases to the cardiac cycle. And as we are going through those phases, we want to pay attention to the pressure in the atria versus the ventricles, right? So we have our 4 chambers, right? Okay, our atria on top, our ventricles on the bottom. I'll just label right atrium and left ventricle. That should be enough orientation here. Okay, so we're going to be paying attention to the pressure in each of these chambers. We're going to be paying attention to the pressure in our blood vessels, specifically the pressure in the aorta, which is that arc leading us out to the systemic circuit, right? So out to the body, out to our organs. Pressure here is going to be important. We're also going to be thinking about how much blood is in these places, especially in the ventricles. Because that ventricular blood, specifically in the left ventricle, is what is going to get pushed out to all your other organs. And we're going to see that what's going on with the blood movement is also what creates heart sounds. So like when you're listening to the like lub-dub rhythm of the heart, that has to do with these pressures and flow in the heart. So we're going to see all of those kind of linked up in the cardiac cycle. Okay. So by definition, what the cardiac cycle just is, are all the events that are associated with the flow of blood through the heart in just one heartbeat. So the cardiac cycle is really just telling you one single heartbeat. We focus on the ventricles. So like, I kind of think of the cardiac cycle as being almost from the perspective of the left ventricle. We'll think about the other chambers as well to explain what's going on. But I'm pointing out that we care about the ventricles because systole and diastole are defined specifically by whether the ventricles are contracting or the ventricles are relaxing, right? So while our atria do contract and relax as well, when we're looking at these two major periods, that is from the perspective of a ventricle. So systole, like to think S, stress, contracting. Diastole is that relaxation phase. Okay. So our valves are going to basically be our doors directing blood flow or really preventing backflow. So our valves between our atria and our ventricles, and also between our ventricles and the great vessels, which are pulmonary trunk leading into those pulmonary arteries, and our aorta leading out to the systemic circuit. All of those are going to open passively, basically when we have blood pushing on them from the correct direction. Okay. So if we're thinking about an AV valve, an atrioventricular valve, okay, draw it a little different this time. Okay, so we've got these doors basically between our atria and our ventricles, right? So when we have a high pressure in, let's say, the right atrium, high pressure. Okay. Okay. There's high pressure or higher pressure in an atrium and lower pressure in the ventricle, in that right ventricle, because that's the one it's connected to. Okay. We're just going to go from high to low. We're pushing on that door. We're pushing on that valve in the correct direction. So it just opens passively. Okay. Now, if we're thinking about a semilunar valve, the semilunar valves go out to the blood vessels, right? So I'm going to put an aorta on here. Okay. The semilunar valves were the ones that had those cups for blood, right? The ones that go like that. Right, so they're curly, they can inflate. Okay. So these are going to open up when, I'll label this left ventricle, right? When we have higher pressure in a ventricle. Versus lower pressure in the artery. Okay, that's what opens the semilunar valve in the correct direction. So the valves work differently. We don't want our valves to collapse in the wrong direction. So we're always going to control the flow of blood in these two specific directions. So those are the two directions where we can passively open. If the blood is trying to go the opposite direction, say we have high pressure in the artery, low pressure in the ventricle, it would try to backflow. This valve would shut. Same thing would happen when we have high pressure in the ventricle relative to lower pressure in the atrium. Blood tries to push back, closes shut, and we have chordae tendineae and papillary muscles to prevent it from prolapsing all the way into the atrium. Right, so we have mechanisms to prevent the flow of blood from going the wrong way. So for our phases, we are going to start our phases of the cardiac cycle from the perspective of the ventricle, specifically because we're really interested in like that left ventricle getting blood out to your organ. So we are going to start actually in the middle to the later part of its rest phase. So the cardiac cycle we're thinking of as starting as we're filling the ventricles, right? So we're filling the ventricles. That's our first phase of the cardiac cycle. And this is happening when your heart is at rest, right? So this is that relaxation period, okay? So what's happening here is we have blood returning to the heart, and we have blood coming from those atria and going into the ventricles, okay? So during this ventricular phase, we're going to need those AV valves to open. So we need the atrioventricular valves open because otherwise we can't fill a ventricle at all, okay? And the blood is moving in its correct direction from an atrium to a ventricle. That's our direction of the blood, okay? And we don't yet want that blood to flow into the arteries because we're trying to fill the ventricle, right? So we don't want stuff escaping. So at this point in time, the valves, those semilunar valves going out to our arteries, the pulmonary trunk and the aorta, are closed. Okay. Now, this is a passive process until the atria contract. Okay, so on this image, we have like everything kind of linked together. So in the images, it's showing us our flow of blood. So we've got arrows for flow of blood. Okay. We've got our phase numbers, right? Phase numbers here. We have part of this figure that tells us the state of those valves. So AV valves open during phase 1 are ventricular filling. Our semilunar valves, the aortic and pulmonary valves, are closed. Okay. We can see what is happening with our pressures. Okay, so we can see here, we're not talking about it yet, but pressure in our aorta is decreasing a little. We have slight rises in the pressure in the atria and the ventricles because they're filling with blood. And when you have more volume in a chamber, like it's more crowded in there, that creates more pressure. Okay, so that's what's going on here. So you can see that that's paired up here with this increase in volume of blood. Okay. And during this filling phase, we don't have any heart sounds happening. So if you were listening with a stethoscope to the heart, no heart sound. If you were looking at an EKG, you would see somewhere in this first phase of the cardiac cycle is when you would see that atrial contraction, that depolarization of the atria as they contract and push a little bit of extra blood into the ventricle. Now, our second phase of the cardiac cycle is going to happen when we close off our chamber, we close off the ventricle, and we start to contract. So this is the start of systole. So that stress phase, that contract. Now, we are going to have multiple phases that do occur during systole. So this isn't all of systole. But we can see in the name, our ventricles are contracting. This is going to create increases in pressure. The other thing that we can see happening here, right? In this name, we have isovolumetric, right? So what this means is same volume, right? So same is iso, volumetric is volume, right? So what this is referring to is that during this second phase of the cardiac cycle, this isovolumetric ventricular contraction phase, we don't have the amount of blood in that ventricle changing. That's what volume we're talking about. We are not changing the volume of blood contained. What we are changing is how contracted the muscle is, and therefore the pressure that is on that blood, okay? So in order to have this happen, this means that we have to have a closed chamber, right? Like if any of our valves were open, right? And you squeeze, you have a door open, you have a valve open. Think about squeezing a balloon, right? If you have a hole, that blood would escape out the hole. It would stop the pressure from rising all that much. So during this first, and if there is a hole and you have stuff escaping, it wouldn't be isovolumetric. You'd see a decrease in volume because the volume is just how much blood. Okay. So we have a closed box for our ventricle during the isovolumetric ventricular contraction so that we don't change the volume. So both our AV valves, the valves between the atria and ventricles, and those semilunar valves, the valves out to our arteries, are closed. So there's no blood entering, there's no blood exiting. All that we're changing is that muscle contraction and therefore the pressure inside that ventricle. So you can see here that this is a pretty short phase. Eventually the pressure is going to get big enough that blood starts shooting out, basically. Okay. So here we can see that ventricular pressure spiking up. Okay. But our volume of blood is flat. Okay. So here you would hear a heart sound if you were listening to the heart. And the reason you would hear a heart sound is basically as you're squeezing that blood, it would try to push back into the atria, and it kind of like creates turbulent flow around those AV valves. And so that's kind of what you're hearing. You're hearing like swishing blood around the valves when you listen to heart sounds. Okay. We link that up to our EKG. We can see here that we had the ventricular depolarization. So we had like our signal for the heart to contract, and then that ventricle is doing some contracting after that. Okay. Now, valves open when there's pressure, high pressure pushing on them in the right direction. Okay. So the reason that that isovolumetric contraction phase was so short is that as this pressure starts to spike, it very quickly overcomes the existing pressure in the aorta. Okay. So once we have higher pressure in the ventricle versus lower pressure in the artery, okay, this means our semilunar valves are going to open because that's the correct direction for the flow. So those valves are going to collapse against the artery wall. And this means that we actually squeeze blood out. So that's what we're ejecting during the ventricular ejection phase. That's talking about ejecting the blood, right? So blood is physically being squeezed out now. So during phase 2, isovolumetric contraction, we're just putting pressure on the blood. Once the pressure is high enough, it's physically spurting the blood out of that ventricle during phase 3. So for this to happen, we have to have our semilunar valves open. Okay? So our semilunar valves have to be open in order for blood to flow into the arteries. And the other thing that has to be true is that we need those AV valves to be closed, because otherwise the blood would be basically trying to go back into the atria, which are now at a lower pressure as we're squeezing the ventricles so hard. Okay. So specifically, if we're thinking about left ventricle, right, we are trying to press into the aorta. At the end of this phase, you can see that our pressures are about to reverse, right? So the green line was our ventricular pressure. The blue line was our aortic pressure. Okay. So as we squeeze blood out and out and out, we can squeeze blood out so long as our pressure in the ventricle is higher than pressure in the aorta. But eventually we're out of blood to squeeze, right? So there's not that much pressure if you're not compressing anything. So at the very end of this phase, the pressure in the ventricle is going to dip below the pressure in the arteries. Specifically, we're thinking about left ventricle. So the aorta is connected to the left ventricle. So when that happens, we're going to move into our next phase as those semilunar valves close. Okay, so semilunar valves are going to prevent blood from coming back from the aorta to the ventricles, because we're always going from high pressure to low pressure. We don't want to go from the aorta back to the heart, right? We don't want to do that. So we have to close those valves. All right. So that leads us into our next phase. So we can see more clearly here that relationship between the pressure in the aorta and the pressure in the ventricle. So we can see here, this aortic pressure is staying high, right? We've squeezed blood into the aorta. This is where most of our blood is now, stuck in the aorta. Not stuck, but that's where it is, right? Versus our ventricles emptied their blood into the aorta, and now that heart muscle is relaxing, okay? I'm relaxing that ventricular muscle now. Okay, so that pressure is falling, falling, falling. This is the beginning of diastole, that rest phase. Okay, so we're going back to rest as we're resting this ventricle. So overall, our name for this is isovolumetric ventricular relaxation. So we're relaxing the ventricles, and we're doing it in a way where we're not changing volume again. So isovolumetric, again, means same volume. Okay. So what's happening here is that ventricle is relaxing, decreasing pressure, just like in our isovolumetric contraction, that second phase. We have all our valves closed. We've got a closed box. The box is getting bigger, okay, which is why our pressure is falling. No blood is entering or exiting. And then once our pressure falls low enough, we would go back to the beginning, back to our first phase and start filling the ventricle again. Okay. So looking at that overview, let's go ahead and answer a question about these phases. So what we're answering here is we want to know what is happening during the isovolumetric contraction. Okay, so we want to know all of the pieces of this picture when we're learning the phases of the cardiac cycle. So we want to know what's going on with our valves. We want to know what's going on with our contractions. We want to know what's happening in each part of the heart, basically. All right, take another minute to look through and then we'll go over it. Okay. Perfect. Yes. So isovolumetric contraction is referring to the fact that the ventricles are contracting, but no blood is entering or leaving that ventricle, which means all of our valves have to be closed. So that's our AV valves and our semilunar valves. Oh, it's blurry, but this is the overall big picture that we were stepping through piece by piece. I'll make sure that you have a picture that is not blurry for you to study from, but the full picture is probably on that last phase slide. Oh, there we go. There's a non-blurry picture. Okay. So this is that whole picture in order, right? So this is showing us going back to phase one after our isovolumetric relaxation. So in total, what we had happen was our ventricles start to fill late in diastole, so late in that rest phase. So we have blood coming from the atria into the ventricles through an open AV valve. During the end part of this first phase, the atria actually contract, pushing the rest of their blood that can't passively push into the ventricle. Okay. We then see the ventricles contract. So atria contract first, then ventricles contract second. For a period of time, the pressure in that ventricle is not great enough to overcome the existing pressure in the corresponding arteries. Okay, so we have isovolumetric contraction while we have a closed box with our AV valves closed so that we don't have backflow into the atria, but our semilunar valves also closed. So we're not getting blood into the arteries yet. As soon as our pressure is high enough to overcome that arterial pressure, we get into the ventricular ejection phase, which is when we have blood actually escaping the ventricles and getting pumped out to the rest of the body. Okay. And then the heart starts to relax, specifically our ventricles are relaxing for a period of time. All of our valves are closed, so we have isovolumetric ventricular relaxation until we see the pressure in the atria greater than the pressure in the ventricles, when we loop back to the ventricular filling and then start that next heartbeat. Okay. So if we map this onto like our systole and diastole, right? Diastole is like 4 and then 1. And then systole, that contraction part, was 2 and 3. But we start counting from when we start filling the ventricles with blood, which is why we have this kind of offset one. Okay, so we will leave that here for today. The next couple slides are just recapping the same thing anyway. And we'll finish up next week.